I'm Kishore Venkateshan, and this is a combined work with Pranita Naik and our advisor Prabhati and Swami. I bet everybody knows what a life assistant is, a personal assistant is in general. A digital life assistant is just a software program that performs the activities that a life assistant does for its user. So it understands its behavior or his behavior, his patterns, and it tries to efficiently implement his everyday routines. So a benchmark for such systems in speech recognition, using speech recognition and communicating to life assistants, digital life assistants, is Jarvis. It's actually a fictional work from this movie called Iron Man, and it is this highly intelligent system that is able to respond to users with almost a 0.2 second delay, and it's so fast, and it does almost everything from understand sarcasm, make sarcasms, and many other things. It is able to understand gestures and so on. But what we are interested is in the speech part of it, and we'll be trying to solve only one sub-problem of this, which is the responsiveness issue. Everybody uses Siri, everybody uses Google Speak now, and all those new technologies that have been coming up. One thing that is main in all these various technologies that have come up is they use something called natural language processing to retrieve the context of whatever speech has been recognized. In that perspective, I believe that natural language processing has been overly used. So in a simple sentence, you can say that NLP has dominated the performance for any such kind of technologies that involve digital life assistants. Let me give you an example. To find a route from here to a restaurant, I would say find me a restaurant nearby. So there are 3 steps in this. First, there is speech recognition to understand what you're saying, and then there is a natural language processing to retrieve the context of what you're saying, and finally there is an action sequence that says, okay, because this is the context, we need to perform these kind of actions to give the user what he wants. But when I say the same thing again, say I walk 3 steps and I say, find me the nearest restaurant again, it's going to be doing these 3 steps over and over again. But in this, speech recognition is important and is compulsory. Whereas NLP, we think there can be an alternative to NLP that does not replace NLP, but as a pre-processing step to determine whether NLP is required or not. And that's where our approach, the switch state mechanism, will be coming. So if I'm talking about digital life assistants, then I don't think I can proceed any further without mentioning the big players, which is Siri and Google now, and we also have Microsoft coming in recently with their speech recognition systems. But why do we need these is because they have the state-of-the-art training system for speech as well as for natural language processing. On similar grounds, there's also this individual named Chad Barfoot who has managed to accomplish a rendition of Jarvis with his home automation systems. But our motivation comes from this project called Project Alpha. The link is right there. And they use something called Windows speech recognition macros, and they restrict the choices available to the user. So that way, they say that these are the commands and these are the actions that you can be performing. Our motivation is on similar grounds, except we're going to be doing it in a more constrained and in a better, efficient way. The backbone of our system is the finite automata. So I think allow me to review it for a second, because a DFA, or deterministic finite automata, is a set of states Q, and also has a set of input symbols, which is called the alphabet. Now each of these symbols from the alphabet causes a transition from a state Si to another state Sj using this transition function. And then there's a start state Q0, and then there's a set of accepted states to say that this is the final state of the system, or this should be the final state of the system. How do we perceive our system as a finite automata? That is just simple. We just take all the operations of the system or an application or a process group, and we group them into states. So all the similar behavior or applications that require similar types of commands are all grouped into states. In that order, S0 will be our default state, in the sense, say system-specific functions like shut down system, or turn off mute the volume, or increase the volume, and so on. So they all will be grouped into default state, and that will be our start as well as the final state, because That's handling all the system operations that we need. Any other state SI will represent a separate application. For example, we are considering S1 to be a presentation state, which will help the user present without the use of any keyboards or any external devices, for that matter. Within states, we have two types of choices that we are constraining the user to. One is the in-state choices, which will help the user control the application with his voice commands. As well as we have transition choices, which will help the user move from one state to another state. Like if he has to go to presentation from default, then he has to say open presentation mode, and so on. I'll explain default state a little bit later. What is new in our approach, or rather, how are we differentiating from DFA in switch state mechanism? Consider a system in state X, and then there's an input A that comes to state X. Then our system moves to state Y. So every new symbol in the alphabet will now operate on state Y. So as you can see, a symbol B will take it from Y to Z, but there is no operation on X. So X is just sitting without any use right now. In our system, we rectify that because we know that a user might require another application as well. So we rectify that by giving a symbol transition from X to A as well. And how we are doing that is we are using switch states. Instead of regular states, we are using switch states. The difference is every state on transition carries a value called the switch value. And now this value can be a 1 or a 0. 1 implies that the choices are retained after transition. So if you transit from X to Y and you set the switch value to 1, then the operations are still applicable on X. So that's what the switch value 1 means. Whereas the switch value of 0 implies that you don't need X anymore. The X is not part of the system anymore, so the user has no connection with X as such. Any transition that occurs from state SI to SJ is given by this AIJ of X, where A is one of the transitional command or the input command. And I and J are the states SI and SJ, and X is the switch value that SI should be set to. Let me demystify the system a little bit now because I think I introduced too many terms. An example would be a better way to do it. As I said, default state has to be active throughout the system because every transition or every application is open from the default state, so it needs to be active all the time. Having said that, now say I want to open the presentation mode and I say open presentation. You can see that the input symbol is A01, where A is open presentation, and 01 is from state 0, which is default state, to the presentation state, and the 1 sets that default state should be active for the rest of the execution of the system. Now when I get to presentation state, now presentation state has its own table of commands that the user can input, or that the user is allowed to speak to the system in that state, in presentation state. But do note that default state options are still applicable, so the user can still switch from default state to any other application that he wishes to. Now from presentation state, now say he wants to get to editing, like he wants to edit presentation, he wants to add some shapes or add some text to the presentation. He would say edit presentation, and that would take us to presentation editing state. Now note that the input symbol is A12 of 0, which means I'm saying that the presentation state commands are no longer applicable. And that's reasonable because if he's in editing state, then he wouldn't want to close the system without saying save first, or for that matter, he wouldn't want to run the slideshow while he's still editing his presentation. So that settles that. So A12 of 0 says that presentation state commands are no longer applicable, and only the presentation editing state and the default state as usual is applicable. So now, say he quickly wants to change music or anything that he's listening to. Now he'd say music player, he would get into the music state, and then he would quickly perform a command, and that would jump right back into the default state or any current state of application that is. This happened. The same steps can be applied for any other application or process group, say SI through SJ, and they all work in a similar function. Now, I think many of you would have already realized that there's a huge hazard over here. That is, what if the user leaves too many dangling states? That is, he leaves too many applications open. So we need to account for that. We need to say that the choices should not keep increasing over time. If the choices keep increasing, then the error rate is too much, and that's what we face currently. That's why we use NLP. But we are trying to determine a pre-processing step to NLP, so we need the error rate to be minimum. Having said that, we have these options, least recently used algorithm, the most recently used algorithm, and the first in first out algorithm. All these are directly from the OS operating system concepts of cache maintenance. So we could use the similar techniques over here as well to determine which the user wants and which states should have their choices retained for the user to speak to the system. We selected the LRU approach, the least recently used approach, because it seemed to be reasonable during our time of application. We created a small implementation using whatever we described here. We call it the J24 system. It contains 22 different states. That is, it is able to access 10 different applications, and each of these applications have substates further, like how I did with the presentation. And approximately 70 to 75 commands in each state. Some even have 100, 120, like the default state. These are for the operations of that particular application or that particular state. And then we also have 15 to 20 other transitional choices, like move to this state, move to that state, and so on. This was tested on 5 anonymous users who were oblivious to the fact that they were being tested. So as you can see, the graph suggests that, the graph is x-axis x-axis is days. It says day 1, day 2, day 3, day 4. So we tested them for 5 days. And on the y-axis, you have the new commands for every 100 commands that they have spoken. On an average, there are about 70 to 75 new commands that they speak for every 100 commands. That's during day 1, but and that was a hideous result. But as we went ahead onto day 2, day 3, and so on, we noticed that they subconsciously kept repeating themselves. So that way, we were able to create a better cache system to store these commands and execute them if they say it again. And that's day 5 for you. That's 40 commands for every 100 commands, and it's bound to improve as the days progress. I'd like to conclude by saying that this is much better than doing continuous NLP for every command that's being repeated over time. So that way we can say that switch state mechanism is a good alternative to NLP, or a good way to determine if NLP is required or not for the given set of input commands. Thank you.